Surface integration involves finding the flux over a surface. In this case, we're using an example from section 19.2, problem 9. Our function will be x I hat, y j hat, z k hat. And we'll be integrating over the region of this cylinder, centered on the y-axis from y equals plus 3 to y equals negative 3, the radius of 2. Now, one thing that makes these kind of problems much simpler is to pick the correct coordinate system. A coordinate system can make this problem much easier or much harder. We might start off using, on the endpoints, a Cartesian system. Or we could also do it with a cylindrical system. For the endpoint, for the ends, we have the integral of y of x I hat plus y j hat plus z k hat dot j hat. Now, this gives us the amount of flux that's coming out of the ends, namely this one in particular. The dot product simplifies the situation, leaving us with just y integrated dx dz. At this point in time, since our variable of integration, our variable and our variable of integrations are different, we can simply evaluate this as y dA, where the area is going to be y times pi r squared, r equals 2, y equals 3. We get a value of 3 pi 2 squared gives us 12 pi. Likewise, the other endpoint, pardon that, we can write as xi hat, y j hat, z k hat dot minus j hat. Notice, because we are going out the other side, these arrows are perpendicular or normal to this end. So when we integrate this, we get negative y dx dz minus y, or simply over an area at this point. We end up with, but since y equals negative 3, we once again get 12 pi. Now, the cylindrical outer boundary we have right here is a little bit more complicated. Now, since x and Cartesian coordinates worked so well first time around, we might be tempted to try them again. However, for this particular symmetry, well, we certainly could do it in Cartesian coordinates. Nothing can stop us. It's much easier in cylindrical. It's much easier. In this case, we'll write out our function However, the trick is we always need a perpendicular vector to the surface. In this case, we write it out as cosine theta I hat plus sine theta k hat. Also, we need to be careful with the differentials at the end. Notice, because we're doing it in cylindrical coordinates, we have r included. Now, one thing to not panic about is the fact that we have miscellaneous different variables in here that we have not accounted for. This is quite common, and we simply need to take into account what these variables are equal to. First, let's simplify. Or no, first let's simplify. Let's take this dot product, and we will get our I hat x cosine theta r dy d theta integrated from as our variable order of integration does not matter. Yeah, it doesn't matter. That's okay. We can go from -3 to 3, 0 to 2 pi. Likewise, we can set up our k term as z sine theta r dy d theta. Now, since we have everything in terms of y and theta, we need to find out what these are equal to. We can define, when we set this up, we needed to set this up cosine in terms of x and z, a ratio, and r. So we'll write cosine theta as x over r, in which case we get, x cosine theta r becomes x squared. Likewise, in this case sine, and notice when we're operating this, we're doing this in terms of z and x. So sine is z over r. Writing our functions, our triangle, in terms of the x and z. So z sine theta r becomes z squared. Notice that the radius here is r, hence x squared plus z squared, not y squared, z squared, is r squared. That means we can write these double integrals as x squared plus z squared dy d theta equals r squared dy d theta 0 to 2 pi. Now we simply need to evaluate this function, which will give us a fresh sheet of paper so we don't crowd ourselves. Always a wise idea to get a fresh sheet of paper rather than try to crowd yourself. Clear writing leads to clear thinking, oddly enough. So you're ever stuck on a problem, the first thing to do is get a fresh sheet of paper. Okay, to finish this problem. Since r is not one of our variables of integration, and is independent of these two, we can put r squared 0 to 2 pi d theta minus 3 to 3 dy, where r is 2. Our theta integral gives us 2 pi. Integrating dy from negative 3 to 3 gives us 6. And we have 4 times 6 times 2. That's 8 times 6, that's 48 pi. Which means we have 12 pi plus 12 pi from our ends plus 48 pi gives us 72 pi as the total flux through our surface, being the surface of the cylinder.